So, good morning.
Good morning.
So, like we said, now we are going to look at the multi-conductors, and that we are continuing from where we stopped last time. So everyone can see my document there that I'm sharing.
Yes.
So, what we'll be looking at now is to look at the TEM modes, and we are interested in the distributed parameter analysis of these lines. So for the TEM mode of propagation, we know that we already saw that we can characterize it with a unique voltage and current waves, as we saw for the parallel plate transmission line last time. And the field distribution is of course similar to that of the static case, because we saw that in a transverse plane, the transverse component of the electric field and the magnetic field are all rotational, and this reduces to the static case that you already covered in the third year. So the transmission line can hence be regarded as a distributed parameter electrical network with per unit length shunt capacitance C prime and series inductance L prime, accounting for the energy storage in the electric and magnetic field respectively. We also have the per unit length shunt conductance G prime and the series resistance R prime, which account for the losses in both the electric and the conductors respectively. Now, the parameters can be determined from the distribution on the line, that is the field distribution on the line. But for this particular time, we are just going to satisfy ourselves with the following results obtained from integration. But I could always refer you to the electrostatic case when you are dealing with the field stored in the magnetic field or in the electrostatic field and the magnetic field as well, which we saw was an integral of an energy, density, and so forth. So what we are going to put here is that we are going to use an energy storage parameter, L prime and C prime, which will be given as the permeability, magnetic permeability of the medium divided by the amplitudes modular squared and the integral over the surface of the magnetic field intensities magnitude all squared, okay, over the cross section of the line. We are using a quarter here because for sinusoidal waves, we have, of course, the half which comes in because of using the amplitude rather than the root mean square rather than the amplitudes in the definition from circuit theory. And also the other half will come from the integral of the sine squared or cos squared that will appear in a sinusoidal kind of field here. And that's why we are using a quarter of I naught star L prime equal to the energy Um in the magnetic field, and similarly for the capacity or the electric or the energy stored in the electric field in terms of the capacitance and the voltage amplitudes. So the loss parameters R prime and G prime will be expressed as the R prime is going to be given by the resistance per square divided by the current, the magnitude of the current squared over the surfaces of the first conductor and the second conductor. And we are integrating this over the cross section of of the two conductors and multiplied by the magnetic field intensities squared, that is the integral over those surfaces. And for the shunt, we are going to integrate using the displacement current, and we are going to get it as omega epsilon double prime over V naught multiplied by V naught star. Remember, V naught and I naught are amplitudes of the currents from the circuit theory problem, and these are the fields. So for the analysis, we'll consider a short section of line of an infinitesimal length delta S as shown below. That is, we are going to have a two-conductor transmission line as usual, and we are going to take that section of delta S, and we look at a current. The current wave is coming from the left and is entering our section as IZ of t, and at that point we have also a voltage Vz of t, and leaves the section as as IZ plus delta Z of t, and the other one, and the voltage will be V of Z plus delta V of Z at this point. So these lines you see put on at the points or the ends of the sections are important and are usually called the reference planes for all measurements that we'll be dealing with. And therefore, whenever you are going to be using transmission lines, or when you draw a transmission line section, I expect to see you putting these dashed lines at the reference planes. It's very important because we shall see, as if we were to measure the line characteristics at a different point from the planes so defined, we'll have to add in extra quantities to the values that we compute. So from circuit theory or a distributed or a network, electric network, therefore we have a current IZ represented as a phasor and a voltage VZ across the input to the section as a phasor as well. And we have now a total inductance L prime multiplied by delta Z, because L prime we have said is an inductance per unit length, and this is resistance per unit length multiplied by the length of the line section delta Z, and we have a current IZ plus delta IZ leaving the section at the point Z plus delta Z there, and a voltage across there which is Vz plus delta Z, and therefore the total conductance is given as G prime multiplied by delta Z, and the total capacitance is C prime multiplied by delta Z. So this is a value or a model that you have already covered in the ECT of the idea, and we can see that either whether we are using electrodynamics or we are using that ECT, we are just talking about the same things. So we let the current and the voltage at the sending end be IZ of t. The sending end is the input of the line section. That's what we'll be calling it. And the load end or the receiving end will be the output of that line section. So the voltage across that input is going to be given by Vz of t. And I'm using here the time representation of the quantities, because this is the most general, because we don't have to worry about whether the currents or the voltages are sinusoidal. We can get a general variation with time. So we let the corresponding quantities at the receiving end be given by Iz of t plus delta Z d dz of Iz of t. Here I've used a binomial whatever expansion for that value, and the V of Z equal to that plus d dz of Vz of t respectively. So from Kirchhoff's laws, we can write that V minus V plus V dz d dv of dz is equal to I of zt plus multiplied by R prime, that is the total resistance, plus the change or the voltage across the inductance, which is given as the inductance multiplied by the rate of change of the current. Or in other words, you can write that as dV dz is going to be given by the minus of I Z of t R prime minus L prime di dt. And similarly, for the current, we can write it as I minus I plus delta Z di dz equal to V plus delta Z dV Z at the sending end and multiplied by the total conductance at that point, plus the displacement current, which is the current of the total capacitance multiplied by the rate of change of the voltage at that sending end. Remember, here we are not worried about the dV or the di dt at the other end. Here we are worried about the dV plus delta z or dV dz. We are differentiating the voltage at the corresponding terminal. Now, since delta z is sufficiently small, that is, we have already assumed that delta z is infinitesimally small, then we can ignore higher terms in this integration, and we just get that di dz is just going to be given by the minus of the voltage multiplied by the conductance minus the capacitance per unit length and multiplied by the rate of change of the voltage with respect to time. So we differentiate the voltage equation with respect to z and the current and the current one with respect to time to obtain the following: that d2 dz dz squared of v is equal to the minus of r prime di dz minus n prime d dz of di dt. And for the current, which we are differentiating with respect to time, we get that d dt of di dz equal to the minus of d prime dv dt minus c prime and d2 of v dt square. Now, what we are going to do here is to assume that our transmission line is composed of linear operation, and therefore the order of integration will not, the order of differentiation does not matter. That is, we can differentiate either with respect to z first, and then followed by the differentiation with respect to time, or we could always do the same, that we differentiate with respect to time and then differentiate with respect to z later. And these two values should not be different. And therefore, if we substitute the value of d dt or d dz di dt in this equation here, that is from down here, that is using that value, and we use it in there, we get that the d2 dz squared of v is equal to the product of the resistance and conductance multiplied by the voltage. And we note that this other side, we just have a voltage differentiation with respect to distance, and therefore this is a resistance with respect per unit length, and that is a conductance per unit length, and therefore we see that this product is going to be per meter square or per distance square, okay? And it will have no other dimension. And we can see that this side will be V over area, and that will be V over area. So at least for the first time we are okay. Plus, we have now R prime C prime plus L prime G prime, and we get dV dt, and plus L prime C prime d2V and dt square. So those you can convince yourself that the total, all these values here are going to be in terms of voltage per unit area, okay, all through by doing a dimensional analysis. So if we rearrange this, we obtain the following, that the voltage, okay, we can put all these under the same kind of as an operator and multiply that one by V Z of t is equal to 0. And this is in the form of a wave equation, which in terms of the voltage at the point Z down the line, and will be called the telegrapher's equation for the line voltage. This is exactly in the same form that you have found in the usual, in your third year formulation. The general solution of this wave equation is going to be given by a propagating wave of the form Vz of t equal to the real part of Vz exponent of j omega t, where Vz is the phasor value of the voltage, and will be given as a positive z propagating wave component plus a negative z propagating wave component v minus exponent of gamma z, okay, and will be called the line voltage phasor at the point or at the plane z down the line. And the gamma is going to be given by the product of R prime plus J omega L prime multiplied by G prime plus J omega C prime for sinusoidal values. So that is sinusoidal voltages and current. We'll get that as a product, or in other words, you can have it as the omega into root L prime C prime into R prime G prime by L prime C prime minus 1 plus that imaginary part there, and will be called the propagation constant all the line. So if R prime and G prime are small, and this would often be the case if we are using very good conductors and very good dielectric, that is almost perfect dielectric and almost perfect conductors, then we shall see that the product R prime G prime is going to be small, and therefore we can just get gamma being given by the approximate J omega L prime C prime root 1 minus J 1 over omega into R prime times over L prime times G prime over C prime. And using the binomial expansion of these values, that is, we are assuming that this value here is much smaller than unity, then we can use the binomial expansion and keep only the first two linear terms, and we obtain that gamma is going to be given by J omega root L prime C prime into 1 minus J 1 over 2 omega R prime over L prime plus G prime over C prime. And if we were to multiply through, we'll see that this will give us an attenuation constant, that is a real part alpha, and this will give us the imaginary part, which is J omega root L prime C prime. And with this we recognized as the propagation constant, or the phase propagation constant for a lossless line. So this is what I've just said a few minutes ago. That is, we can write it as alpha plus J beta equal to a half into R prime by root C prime by L prime plus G prime root L prime by C prime plus J omega root L prime C prime. Now we are going to use this L prime and C prime as the lossless case, okay? That is the inductance and capacitance per unit length for a lossless line, and therefore you are going to define a characteristic impedance Z0 like we did before as the square root of L prime by C prime, but then we shall see that for a line, the characteristic impedance is going to be different from this value here. And therefore, if we were to do that, we can always write this equation in this form, that is going to be a half of the resistance per unit length normalized to the characteristic impedance for the lossless case plus the conductance per unit length normalized to the same impedance plus J omega root L prime C prime. And here I saw that many of us don't know how to make analysis or analogies, especially for the fourth question in the exam. Nobody could get the equivalence of parameters, okay? All we are saying is that if we compare, then the real part of this, that is alpha, is just going to be given by a half R prime over Z0 plus G prime multiplied by Z0. And beta must therefore be given by omega root L prime C prime. So the line current phasor at Z is also going to be given by the same value. That is, if we were to start with the current, that is, instead of substituting the current into the voltage solution, or this voltage equation, we substitute the voltage equation into the current equation, we'll get a similar wave equation for currents, and we'll get as a general solution of a positive Z propagating current wave plus a negative Z propagating current wave given as that. And this can be given as the gamma of R prime plus J omega L prime, that is the series impedance per unit length, okay? That is a propagation constant divided by the series impedance per unit length, and multiplying the voltage phasor form. And therefore, the parameters I plus, V plus, and I minus, V minus are the incident and the reflected wave amplitudes respectively. And the reason why we are using incident and reflected is because when we started the analysis, we assumed that our current was entering the line section from the left, therefore traveling in the positive Z direction, and therefore any current that is moving backwards must be reflected. Okay? So incident and reflected is just because of the structure that we are analyzing. So we'll define a characteristic impedance on the line as just the value, okay, only when we have one wave or one wave component propagating on that line. That is, if the line was infinitely long, then we would get only the positive Z propagating wave components alone. And if we take their ratios, V plus over I plus, would get a characteristic impedance Z naught prime. Z naught prime is because we know our line is lossy, and therefore it's not going to be the Z naught of the lossless case. What we can say is that this value of minus is that you start first of all with the current wave, the voltage waveform or the voltage equation and the current equation. And if you look at them, the current is related to the voltage through a differential, and therefore we'll have a minus sign there. So that's why always we get a minus V of minus over I of minus. Just like the way we saw for the field waves that hit a dielectric or a planar boundary on that line or in the media. And therefore, we can write that Z naught prime is going to be given by the series impedance per unit length divided by the propagation constant gamma plus, and it's also going to be given by R prime plus J omega L prime over G prime plus J omega C prime. That is the series impedance per unit length divided by the shunt admittance per unit length, and we can give it as that value. Okay, since the gamma is just going to be given by that equation there. I think here there is something missing with the square root sign, and I'll be correcting this as we go along before I post this again. So this one lacks a square root sign. So this is unfortunate for me. I'm just noticing it now. So in the loss-free case, we saw that alpha is going to be equal to 0. And therefore, we can see that the gamma is just going to be the J beta, and this must be given by J omega root L prime C prime. And Z naught prime is just going to be given by Z naught, which we have defined as the square root of the inductance per unit length divided by the capacitance per unit length. So, if we consider, we want to see how the capacitance per unit length could be computed. So we consider a two-conductor structure as shown there with the coordinate system as indicated, and we have as our conductor 2 at a voltage potential V0 by 2, and conductor 1 at a voltage as a potential minus V0 divided by 2, so that the potential difference between the two conductors is just simply V0. Now, what we are going to do is that we are since this one is assumed to be positive and that is negative, then the line fields or the fields of electric intensity, field intensity will be normal to those conductors. If we assume that the conductors are perfect, then they are going to be normal everywhere, and they'll be as shown there. And therefore, at the center or some point P1 between the two lines, we have a plane of potential equal to 0 line. Okay, so the fields will be going around the conductors. Okay, that is the magnetic field. The electric field is normal to the surfaces and bulging out or through the others. So, in the loss-free case, the charge on the conductor surfaces can be determined from the normal component of the electric field as rho s equal to the epsilon multiplied by the normal component of E, which is just going to be equal to the minus of the epsilon multiplied by the unit normal, outward normal on the conductor dot the gradient of phi of E. That is, phi of E is of course the potential, the electric scalar potential, and we know that E can be defined as the negative of the gradient of the potential there. And this is going to be given by the minus of epsilon d phi differentiated over the unit normal. And therefore, once the potential has been determined, we can always get the value of the surface charge density on the conductors. So the total charge per unit length of the line on one conductor, say for example, the conductor S2, is then going to be given by Q prime equal to the surface, the closed surface integral over that, the surface of that conductor. And we can see that that's just going to be given by the epsilon of n cap dot E dl. And that on S1 is going to be the negative because of the voltage that we have at the bottom. So since the potential difference between the conductors is V0, then the capacitance per unit length of the line is then going to be given by C prime equal to Q prime over V0, and this is equal to that integral over the integral over the path from the first conductor to the second, from the second conductor to the first conductor, to remove the minus sign, and we get E dot dl, where dl is an integration, a path, an element of path on a line, along a line of flux. The total current on S2 is of course from Ampere's Surface law, the integral, the line in, the surface integral of H dot dl all over that line, that surface, and we get that is going to be given by the line integral of the divided of E over 1 over eta. That is, we are dividing it by the impedance, which we are assuming is not changing with position, and we get Q over epsilon eta. And therefore, this will hold because, one, we have seen that the magnitude of the magnetic field intensity is just going to be given by the magnitude of the electric field intensity divided by the impedance, intrinsic impedance, and this can be given as the total or the normal component of E divided by eta at the surface S2. And the tangential component of the electric field and normal component of the magnetic fields are separately equal to 0 on the perfect conductor. So the characteristic impedance of the line will then be given by V0 divided by I0, and we can see that it's going to be V0 by Q prime epsilon eta, which is just that is epsilon divided by C prime and multiplied by eta. So the tangential component of H and the tangential component of E are orthogonal, and hence the magnetic field lines are coincident with the equipotentials of the electric fields. So all flux lines from the phi equal to 0 equipotential to phi equal to V0 by 2 in the two conductor line will link the current in S2 alone. And hence, any path, P1 being the point on the phi E equal to 0 line, and to S2 or P2 S2, orthogonal to the flux lines, will coincide with a line of electric force, and the flux cutting such a path is then going to be given by psi equal to the integral for P1 to S2 of mu H of t dl. And this is going to be given by mu by eta into the minus of Et dot dl, which gives us a value of mu by eta V0 by 2. And therefore, the inductance of one conductor is going to be given by the magnetic flux linked by linkage for that conductor divided by the total current, which is psi over I0 equal to mu by that and V by that, eta naught. And we get this is going to be Z naught. And the inductance for both conductors will then be twice this value if we are assuming conductors that are the same. and we get an N prime equal to mu by eta of pi by z naught. From which we can see that the intrinsic impedance is just going to be given by mu by over L prime z naught, and this is the same as C prime by epsilon and multiplied by z naught. So the dielectric has a complex when the dielectric is lossy, it will have a complex permittivity, which will be given by epsilon equal to epsilon prime minus j epsilon double prime, where the epsilon double prime will include all the effects due to non-zero conductivities of the dielectric, as well as the polarization damping forces. So the total shunt current then will consist of the displacement current and a conduction component. So the current leaving S2 per unit length of the line will then be given by I equal to the displacement current plus the conduction current through the non-zero conductivity, and that being the displacement due to the polarization. And this will be given by j omega epsilon, the line integral on S2 multiplied by the field, the electric field, that is dot MdL, and we get that value there. And we see that it's just going to be given by the displacement current, that is j omega epsilon prime, multiplying that electric field, plus the conduction current, which is related to omega epsilon double prime. So the total shunt admittance is therefore going to be given by the j omega c prime plus the conductance g prime, which is the displacement current plus the conduction current divided by the potential difference. Or in other words, you can see that g prime is just going to be given by the conduction current IC by V naught, which is IC by ID, that is the ratio. We are taking the ratio of ID by the conduction current to the displacement current, and removing that division there by using the displacement current divided by the voltage across the line. And we see that this is just going to be given by the ratios omega epsilon double prime over epsilon prime, and multiplied by the capacitance per unit length, because this is the capacitance per unit length there. And the finite conductivity of the conductors will be accounted for by a series resistance per unit length of line, which is R prime, as long as this is chosen such that the total power dissipated in that series resistance per unit length is equal to the total power loss due to the finite conductivity of the conductors. That is, we are equating the circuit theory value to the field value. And therefore, R prime is just going to be given by Rm over 2, the integral for that value there, and divided by the total current at the bottom. So the further effect of a finite conductivity is to increase the series inductance of the line, since we have seen that the surface impedance on a good conductor, Zm, is going to be given by 1 plus j over delta over sigma multiplied by the skin depth. Remember that this is only true when the conductor has a thickness in the direction of wave propagation, or the field propagation, that is much thicker than a skin depth. And this can be reduced as a series resistance per square plus a series reactance per square chi m. And when we look at this, you can see that chi m and Rm are equal. So the imaginary part of Zm will come from the fact that the magnetic field will now be penetrating the conductor, and the magnetic energy stored in chi m therefore going to be given by U of m equal to xm by 4 omega and integral of that value there. That is where this is the surface current density, okay, which is obtained from the tangential component of H, where we can now write that Lm, that is the inductance associated with the reactance Xm is going to be given by Xm over omega, and it's going to be given by Rm over omega there. This is usually called the internal inductance of the conductors, and this appears whenever the conductors have finite conductivity. Therefore, the total energy stored in the magnetic field is going to be given by Rm over 4 omega, which is equal to Rm over 4 omega, R prime I naught by Rm equal to just R prime by 2 omega and multiplied by I naught over square root of 2 all squared. Now, this gives us the RMS value of the current, and therefore we can see that this is exactly what we get for the energies. So we therefore define a skin effect or an internal inductance Lm per unit length through that value there, Lm I naught squared over 4 equal to U of M, and therefore we can get that omega Lm is equal to R prime. So because of the series inductive, because of this skin effect, the series inductive reactance of the line will be increased by an amount equal to the series resistance that we have in that conductor. And therefore, when you are going to be designing communication links, you have to worry about the conductivity of your line, because this will affect the values of the inductance per unit length. But fortunately, in many cases, most of the time, that Lm is usually much smaller than the self-inductance of the line, or the external inductance of the line, which we replace by L prime, okay? For all practical, for many of the frequencies that we'll be interested in driving that conductor or that line with. So we can illustrate these ideas using the coaxial and the two wire lines to get a feel of the magnitudes that we are talking about. So for a coaxial line, we have that the potential phi of E is going to be given by the potential difference B naught between the inner and outer conductors, and it will represent, it varies by the distance, that is the distance from the origin or the axis of the line, as the natural log of R by B and over natural log of A by B. And the charge is given by the integral from 0 to 2 pi, okay, from multiplied by the rate the electric field, which in this case is going to be purely radial between the two conductors, okay, and multiplied by the arc. The path of the dl here is just going to be the radius of the inner conductor, and multiplied by the angle subtended at the axis, and we get a value that is given by that value there. And we get a value of 2 pi epsilon V naught by natural log of B by A. And therefore C prime is just going to be given by that that whatever ratio we get, that is going to be epsilon prime by epsilon prime over Q prime by V naught, which is equal to just 2 pi epsilon over natural log of B by A. I think there is a problem with this epsilon. It should not be appearing here at all. That one should be removed. So the magnetic field is given by H equal to the actual value of the voltage there. That is the component, that is the amplitude of the magnetic field intensity, multiplied by the propagation. And we can see that that is going to be purely circumferential, that is in the direction of azimuth or algo. And this is given by that equation there. And the current will be given by the integral over the whole circumference of that value. And this is going to be given by twice pi V naught by eta natural log of B by A. This is from Ampere's circuit law. And therefore, can get that the impedance, the characteristic impedance, which is V naught by I naught, is just going to be given by eta by twice pi natural log of B by A, which is just 60 over root epsilon r natural log of B by A, and this will be given in ohms. The reason I have 60 here is because eta, for when we have an air dielectric, that is eta naught, is going to be twice 120 pi, and therefore we just add, if eta, if the medium is different from air or vacuum, all we have to do is to divide the characteristic impedance of free space by the refractive index of the medium, which is root epsilon r. We get that value there. So the flux linking the center conductor is then going to be given by psi equal to mu integral from A to B, and integrating that circumferential whatever electric magnetic field intensity, and we get a value of mu by eta multiplied by V naught. And thus the inductance, which is usually defined as the total magnetic flux linkage divided by the total current, is just going to be given by that value. We get a mu by 2 pi natural log of B by A. And the inductor, the conductance per unit length, we just use what we saw before, that is just the conductance, okay, the conductivity divided by the permittivity, and we multiply that one by C prime, that is the capacitance per unit length, and we get a value of that nature there. So the power loss in the conductors is of course going to be given by a half the series impedance resistance per unit length multiplied by the current, and that is going to be given by Rm pi over V naught over that, and we'll get a value of 1 over A plus 1 over B. And this is what we were saying, that the power loss will be dependent on the values we have there. That is, if we had a very small center conductor, as is usually the case, we can always ignore the introduction of that, and we'll just be dealing with just 1 over A for this particular case. So the series impedance, the series resistance per unit length is just going to be given by that value Rm over 2 pi into 1 over A plus 1 over B all squared into that value there, because we know that these other values here are coming from I naught squared, and Lm, which we said was just the same as the series the series resistance per unit length divided by omega, will get that value. So as the frequency increases, we can see that the internal impedance or the internal inductance decreases as well, and therefore can be ignored for those values. And the total inductance by unit length will be L prime plus that internal inductance, which is given by the external inductance by unit length, plus the value of the internal internal inductance there. And this is the series, okay? That is delta C, delta S, okay, is of course the conductance, and we are correcting it with the geometry of the line, which is the correction line in this particular case. Capacitance by unit length for a 2-wire transmission line will of radius A with a separation D is of course given by the C prime equal to pi epsilon over the hyperbolic cosine of minus 1 D divided by A. The A is the radius of the conductor, and D is the separation of the conductors, which we are assuming in this particular case are equal. And this expression is of course obtained from the electromagnetics, that is FEE 351, 352 that you covered last year. So the inductance by unit length is of course given by the same kind of expression, and the G prime is given by that value, where we are just using the conductance divided by the permittivity and multiplied by the capacitance by unit length. And whenever D over A is much larger than unity, you can always replace the hyperbolic cosine, the arc hyperbolic cosine of an argument x with the natural log of that argument. And therefore, you can always replace those values. And if we assume the surface current density Js to be flowing only in a very thin surface layer of the conductor. That is when the conductivity is very high, and it's then uniformly distributed over the circumference, when the current in each wire will be given by the I equal to 2 pi A, that is the circumferential length, multiplied by the surface current density Js, because this is usually current per unit length. And hence, the power lost in the conductors is just going to be given by a half of I squared multiplied by the resistance, the total resistance of that particular wire. From which you can see that R prime is just going to be given by that value, and we subtract the skin depth, the skin effect resistance. And Js is not uniform over the circumference of the wires in the strict sense. And because whenever we have two wires carrying current, there is always going to be a distortion because of the magnetic fields. They'll start to, they'll start to interact and then they'll push the current distribution, or the current will try to congregate nearer the faces that are facing each other in the two wires, and therefore the Js will not be uniformly distributed as we have talked about. It will be uniformly distributed if we assume that the two wires, because the current must go into the wires and come out of the other wire, then we must assume that those two wires are separated by by a very large distance, so to speak, so that the magnetic fields around each individual wire does not interact with the other one. Okay, so this is the strict sense, and therefore the expressions that we have obtained must be corrected for the case when the wires are close together. So this phenomenon is usually referred to as the proximity effect. Maybe you may have talked about it when you are dealing with the electromagnetics in the third year course. Now, those parameters, looking for them, I'll always assume that you have already done you are already experts at it, and we usually now can understand that is, we can ignore that detail and now try to look at the line, given that the line has an inductance per unit length, L prime, capacitance per unit length, C prime, a resistance per unit length, R prime, and a conductance per unit length, G prime. How would the wave behave on such a line? So if the line is infinitely long, then we must see that there will be no chance, and if we are just sending the wave from the left, then there's no chance that we are going to develop a wave propagating in the opposite direction. That is, all the negative z-directed wave components will have to vanish on that line. Okay? And therefore, the line voltage at a plane z down the line will just be given by the positive z propagating voltage wave, which is V naught plus exponent of minus gamma z, and the current phasor is just going to be given, or the line current is just going to be given by I naught plus exponent of minus gamma z. Remember, as long as our lines are of finite length, we'll always have a possibility of a negative propagating wave component. And therefore, the phasors, that is the line voltage and the line current, must always be given as the sum of a positive going wave component and a negative going wave component as well. But when the line is infinitely long, and when we shall see that we can terminate a short line in a special way such that the reflection is removed. Just like when we were having the reflection-free kind of transmission of fields, by just setting the angle of incidence at the Brewster angle, so to speak, we could get total transmission. So we shall see that even for the lines themselves, this is usually the case. So in that case, the voltage and current ratio is going to be independent of the position on the line, that it will no longer be a function of Z, and we'll call this impedance the characteristic impedance of that line. So Z naught prime is going to be given by R prime divided by J omega plus J omega L prime divided by the propagation constant gamma, and it should be also be given by the ratio of the gamma divided by the shunt admittance of G prime plus J omega C prime. And this, when we replace gamma by the square root of R prime C prime, that is the Z prime multiplied by Y prime, we get that value there. That is the square root of the series impedance per unit length divided by this shunt admittance per unit length. Okay? So, example 1. Demonstrate the analogy between wave characteristics on a transmission line and uniform plane waves in a lossy and unbounded medium. Now, this is exactly the same thing like what we were talking about in the examination question 4. All we are going to do is to write them down and try to make a correspondence of the terms. Now, in a lossy medium, we have that the epsilon, that is the electric permittivity, can be modeled as a real permittivity E prime minus an imaginary permittivity J epsilon double prime. And we remember we say that the imaginary part must be subtractive because we are assuming that our medium is going to dissipate energy, okay? Because it's going to dissipate energy, then that imaginary part must be negative J. And for the magnetic permeability, we also can have a real permeability mu prime minus the loss accounting imaginary part, which is mu double prime there. So Maxwell's curl equations, that is Faraday's induction law and Ampere's circuit law, will then be modified as shown below. That is, the curl of E is going to be given by the minus J omega of the mu prime minus J mu double prime and multiplied by H. That is, it's going to be equal to the minus time derivative of the magnetic flux density. And the curl of H is going to be given by that displacement current, the time derivative of the displacement current, which we have assumed in this particular case is going to be a sinusoidal kind of, or a harmonic time, has a harmonic time dependence. And we are saying that the medium is linear, such that we can always write that the electric displacement D will be given by an epsilon multiplied by the electric field intensity. So that's what we have. So all we have done is to replace epsilon, where we used to have epsilon here, J omega epsilon E is equal to, and that mu is J omega mu multiplied by H. Okay, so we are replacing it by the value there. Remember, usually this would have a conduction current density J, and the current density J is contained in this J omega multiplied by the minus J epsilon double prime, because this we said is an effective permittivity, okay, which includes damping losses due to polarization damping forces, and also the finite conductivity of the dielectric as well, that is sigma. We have all lumped them together there because externally there's no difference in the two effects. So we'll assume that E is polarized in the X direction, so that if E is equal to X cap E of X, and then we can always find that the derivative of that is the curl will just be equal to the derivative with respect to Z component alone, and this is equal to omega mu prime plus J omega mu prime multiplied by the Y component of the magnetic field intensity. And the curl of H is reduced to just a single component there, that is the minus dHy of Z is Z equal to that value, where we have just applied through. Now, if we compare these equations and the equations we have already derived for the voltage waves on the line, we can see that the minus of the gradient of the voltage with respect to in the Z direction is just given by R prime per J omega L prime multiplied by I Z. And therefore, if we do a comparison, we can see that this behaves as a series resistance per unit length, and that behaves as a series impedance or inductive impedance per unit length as well, which is omega J L prime. Okay, and this other one is the same when compared with that. So omega epsilon double prime is a conductance, and omega epsilon prime is a capacitive reactance, so to speak, or susceptance, omega C prime there. So this is the analogy that we expect you guys to be doing. Not that they are going to look alike. You are saying you are looking at them, the forms of the equations are the same, and therefore one must be representing the other. You make that kind of deduction, so to speak. Then, the equations that are governing Ex and Hy are similar, and we combine to form, that is, we can always differentiate with respect to Z and substitute into the values, and this is what we'll get, a gamma squared Ex of Z, and the other one will be a gamma squared Hy of Z, where gamma is going to be given by alpha plus J beta into the square root of a series impedance per unit length multiplied by a series shunt admittance per unit length given by those values. And the intrinsic impedance for the lossy medium for a wave that is propagating in the positive Z direction is just going to be given by the square root of the series impedance by unit length divided by the whatever the shunt admittance by unit length. And because the omegas are everywhere, they cancel, so you are just left with those values there. This we can always correct, and you will see that we have the same values as we had before. So we will now look at what we call limiting cases for the lines. In many cases, very good lines will have the series resistance per unit length equal to 0, and the shunt conductance per unit length equal to 0. That is, we have perfectly conducting conductors and a perfect dielectric between the conductors. So they will have no free charges in the dielectric, and the conductance of the conductivity of the conductors is infinite as well. And in that case, the skin depth approaches 0, and therefore there is no field penetration into the conductor themselves. Therefore, R prime is just going to be 0. And therefore, this lossless case therefore tells us that gamma, that is the propagation constant, which is given by alpha prime plus J beta, is just going to be given by J omega root L prime C prime, where, remember, these parameters are per unit length, inductance, and capacitance. Now, from which we can deduce straight away that if that is the case, then alpha must be 0, and beta must be given by omega root L prime C prime, and the phase velocity on the line is going to be omega divided by beta, which is equal to 1 over the square root of L prime C prime. And the characteristic impedance Z naught prime is just going to be given by the Z naught for the lossless case, which is just the square root of the series inductance per unit length divided by the capacitance per unit length, all taken the square root of. Now, for a low loss line, we are just going to say that we have good conductors. The conductivity is large, but not infinite. The conductors of the per unit length of the dielectric is also not 0. It's finite, it's small, but non-zero, but it's much smaller than the the capacitive susceptance. This is the same thing we were saying when we were looking at the fields in unbounded media. We were saying that if the conductivity or the conduction current density is much smaller than the displacement current density, we can say that that medium is a good dielectric. It's not a perfect dielectric, but it's a good dielectric. It has no losses. Again, we say that if so, and this also follows the same case that the inductive reactance is much larger than the resistive, because the conductivity is large but not infinite. We have a small penetration of the fields inside the conductor, but that contributes very low loss in the ion. So we can therefore use the binomial expansion for gamma as follows: that alpha plus j beta is equal to j omega multiplied by root L prime C prime. We are extracting out that function there, and we just get 1 plus R prime over j prime L prime multiplied by 1 plus G prime by j omega C prime. And when we use binomial expansion there for each of them, that is, this is square root of that and square root of that. So we are just going to get the binomial expansion of the square root of 1 plus R prime by j omega L prime, and take only the first two linear terms, and we multiply that one by the second one, which is 1 plus G prime over j 2 omega C prime, that is taking the first linear terms. If this is not very strictly true, we might need to expand that one to higher terms, but for now we are just going to use the first two terms because we are saying it's a low loss line. And therefore, when we multiply them around, we'll get that there will be a product of R prime by j 2 omega L prime multiplied by G prime by j 2 omega C prime. But since R prime, these values, R prime by omega L prime is small, much smaller than unity, and G prime over omega C prime is much smaller than unity, then this multiplication product will also be much smaller than unity, and we can ignore it. And therefore, we are just left with, again, the first two linear terms, which is 1 plus 1 over 2 j 2 omega into R prime by L prime plus G prime by C prime, just like we got before. And therefore, we are going to distribute this factor through to get the values of alpha plus j beta. So we can see that alpha is therefore going to be approximately given by a half of R prime by Z prime Z naught plus G prime by Z naught, and beta is just going to be given by omega root L prime C prime, which is exactly as in the lossless case, and Z naught is defined as the square root of L prime by C prime. Now, the phase velocity on this line is just going to be given by Vp, approximately given by omega divided by the beta, and you get that is going to be just like in the lossless case. The characteristic impedance, of course, will be given the same way, where we have used the square root of the series impedance by unit length divided by the shunt admittance by unit length, which we have corrected that, and we have taken this one to the top, and then we are going to this value here is not multiplying everywhere. Okay, I think this one has a problem. There is a problem here. It would be the square root of 1 plus R prime by j omega L prime multiplied by 1 plus G prime by j omega C prime raised to minus a half. That will be raised to plus a half. Okay, so when we do the same binomial expansion, we get a value of Z naught into 1 plus 1 over j 2 omega into R prime over L prime minus G prime over C prime. I'll correct this for you. This is not distributed all through. That should be raised to a half, and that raised to minus a half there, because this is at the bottom, this expression for Z naught prime. And we see that we can, since these ones are very small, okay, this is small and that is small, then their difference must be small as well, and we can always assume that this one is much smaller than unity, and therefore say that even for low loss, the characteristic impedance is just going to be approximately that of a free over a loss-free line. Okay. Now, sometimes we have a line that does not distort. Okay, that is, if you look at this expression here, we have r prime by l prime minus g prime by c prime. Even if these ones were large, if you were to make that this ratio is equal to that ratio, then we'll still have that z naught prime is now going to be equal to z naught, regardless of what the values of these ratios are, as long as they are equal. So such a line would be called a distortionless line. So a distortionless line will be one in which r prime by l prime is equal to g prime by c prime. That is, the series resistance per unit length over the series inductance per unit length is equal to the ratio of the shunt conductance per unit length by the capacitance per unit length. And hence, if you were to place that into the expression, the real expression or the full expression of the characteristic impedance, we can put that in there, and we have replaced now the G prime by the product R prime by L prime multiplied by C prime, okay, and added that in there. And therefore, we can see that we can always get the C prime out. And once we do that, we'll see that this value here is just going to be given by R prime plus J omega L prime squared. Therefore, when we take the square root, we just get remaining 1 by Z naught into R prime plus J omega L prime in there. Okay? And we can get this as follows. That R prime, the alpha is going to be R prime by Z naught, and beta is going to be omega root L prime C prime, which is the lossless case, and that is the same, okay, which is just 1 over, the phase velocity is just 1 over root L prime C prime. And the characteristic impedance is just going to be given by this Z naught. There is a Z naught missing here. No, it's not missing. So it's just R prime plus J omega L prime over R prime C prime over L prime plus J omega C prime. And when we correct this one, we just get a Z naught, that is L prime by C prime, multiplying unity, and we just get Z naught. Now, what you have to realize is that distortionless line does not mean that it's not lossy. There will be an attenuation, a finite non-zero attenuation constant for that line, okay? But the phase propagation constant is a linear function of the frequency of the signal, and therefore all signals travel at the same speed, Vp, phase speed, that is Vp equal to 1 over root L prime C prime, which is a constant for the given line. Okay, so it does not distort. It is not a dispersive kind of line. So in general, when you have a lossy line, it will always be dispersive. So I think now my time is up. It's around 10 minutes past. So in case I'll now propose to stop here and continue from from there tomorrow. So in that case, I'm open now for any questions that you may have. Please note, those ones who want to be admitted into class, if you are not able to connect individually, then try to make sure you come early before I start, because once I start, I will never know whether there are people waiting to be admitted into class. Okay, so these guys who are trying to get in after the class is up, I don't know what to do with them. And try to make sure that you liaise with Waweru to correct your email addresses so that you are able to join the class without me having to intervene. So any question before we call it a day? Well, apparently I'm all alone in class. So since you have no questions, then I'll wish you a nice day. And let's meet tomorrow then.
Thank you.
Good day.
Okay, fine. Bye.